All right, let's jump right in. We're going to be tackling a really critical engineering challenge, one that's all about preventing a total disaster. The question is, how do you safely relieve pressure in a system when it's not just gas and it's not just liquid, but this chaotic mix of both trying to blow out at the exact same time?
So let me start with a question for you. When you picture a chemical plant, what do you think is the absolute most dangerous mixture you could possibly have to deal with in an emergency? Go on, think about it.
You know, the answer probably isn't some super exotic chemical you've never heard of. It's actually something way more common. That turbulent, completely unpredictable mixture of gas and liquid that happens during what we call a two-phase flow relief event. And trust me, trying to manage this is one of the toughest, most important jobs in process safety.
To really get why this is such a huge deal, we first need to talk about the fundamental hazard these systems are designed to fight. And that hazard is overpressure.
It's actually pretty simple. Overpressure is just when a piece of equipment, like a tank or a pipe, is under more stress than it was ever built to handle. And if that pressure doesn't have a safe way to get out, the consequences, well, they can be catastrophic. We're talking about a rupture, a total loss of containment, a really major incident.
So imagine all your other alarms and controls have failed. When things really go wrong, this is your last line of defense. It's called a pressure relief device, or PRD. It's basically a valve designed to pop open and vent all that dangerous excess pressure, protecting the equipment, the environment, and of course, the people working there.
Now that sounds pretty straightforward, right? Pressure gets too high, a valve opens, problem solved. But the situation gets incredibly complicated when you're not just relieving a simple gas or a simple liquid, but both at the same time. This is the two-phase problem, and it changes everything.
Okay, so look at this contrast here. Relieving a single phase, all gas or all liquid, it's predictable. The math is simpler. But two-phase flow, it's chaos, it's violent. And here's the kicker. It often requires a relief path that is 2 to even 10 times larger than for a single-phase fluid. Sizing that correctly is absolutely, fundamentally critical.
So why? Why is it so much harder? Well, it really boils down to this one single, incredibly powerful phenomenon. Just think about it for a second. What happens when a liquid that's been held under intense pressure is suddenly exposed to a lower pressure?
It's a process called flashing. The liquid literally instantly boils, creating a massive, and I mean massive, volume of vapor. The best analogy is a can of soda. That pressurized liquid turns into this rush of foam and gas the second you pop the top. Now imagine that same thing happening, but with thousands of gallons of a chemical inside a pipeline.
And don't just take my word for it. The industry standard API 521 spells it out. All that vapor being generated by flashing literally chokes the relief device. It's like trying to force a gigantic amount of thick foam through a tiny little straw. The valve's ability to get that pressure out just plummets, right at the exact moment you need it the most. So if the physics are this complicated, how on earth do engineers actually design for it? I mean, you can't just guess and hope for the best. You need rigorous, proven calculation methods. Yeah, this is not the place for back-of-the-envelope math. Simple equations just don't work here, because as the pressure drops, the fluid's properties, like its density, are constantly changing. To deal with that, engineers need specialized models that can calculate the requirements step by step, all the way through the relief path. And one of the key tools for this is the Homogeneous Equilibrium Model, or HEM. Now, what it does is it simplifies the chaos by assuming the liquid and vapor are perfectly mixed up and moving together, kind of like a frothy milkshake. It's a conservative assumption, which is a good thing. It means it calculates for a worst-case density. This makes sure that the final size of the relief opening is big enough to handle that violent expansion, building in a serious factor of safety. It's way more rigorous than, say, the simplified omega method you see in API 520, which is fine for a quick check, but doesn't handle those density changes in nearly the same detail. Okay, we've talked about the challenge. Now let's really raise the stakes and look at one of the most hazardous scenarios you can possibly imagine, a runaway chemical reaction. So, the really crucial thing here is how the liquid gets hot. In something like an external fire, you get wall heating. It's like boiling water in a pot on the stove, right? The heat comes from the outside in. But with a runaway reaction, you get volumetric heating. The entire volume of liquid is generating its own heat from the inside out, causing the whole thing to boil and swell up violently. This is way more likely to push that two-phase mixture right out of the relief device. A runaway reaction is basically every process engineer's nightmare. It's a chain reaction that just spirals out of control, generating an incredible amount of energy and pressure in a matter of seconds. Designing a relief system that can actually handle this is the ultimate test of two-phase flow sizing.
The problem got so bad that the entire industry came together and launched the Design Institute for Emergency Relief Systems, or DIERS. This project completely revolutionized safety design. It was a massive deal. It moved the industry away from these old, simple, and often dangerously undersized gas-only calculations and toward the rigorous two-phase methods we have to rely on today. Basically, DIERS proved that for these events, you must size for a frothy, two-phase release to have any hope of being safe.
So let's bring all of this together. Why does this deep dive into thermodynamics and fluid dynamics matter so much? Well, it all comes down to sizing for safety.
Okay, so let's recap the critical points here. First, never ever underestimate two-phase flow. It is a completely different beast than single-phase. The real danger is that flashing, that instant boiling that can choke your relief device. To design for this, engineers can't just guess. They have to use rigorous models like OEGM. And for the absolute worst-case scenarios like runaway reactions, the research from DIERS gave us the essential playbook for ensuring safety.
And this, right here, is the bottom line. In this field, a calculation error isn't just a mistake on a spreadsheet. An undersized relief device can literally mean the difference between a controlled release and a catastrophic vessel failure. Getting this right is a non-negotiable cornerstone of keeping our industrial plants safe.
Which really leaves us with one final thought. In a complex, dynamic plant with countless variables that are always changing, the challenge is just immense. It's a constant process of analysis, calculation, and vigilance to make absolutely sure that if the worst should happen, that last line of defense will always be strong enough to hold.